Hello and welcome back. We've been talking about support vector machines and what makes them special. So essentially, it's a change from empirical risk minimization to structural risk minimization. Remember, in empirical risk minimization, we are trying to reduce the error over the training data set only. And that leads us, if you use a linear discriminant coupled with the gradient descent, and we try to minimize the error over the training data set only, that leads us to the perceptron algorithm that we talked about in much detail in the previous lectures. However, we've also seen that classifiers that do empirical risk minimization only can be sensitive to small perturbations in the input feature representation. A small change in the input feature is going to can possibly change the label. For example, for the if you use the red discriminant, then a small change in the input is going to change the label of a given example. And we don't want to do that. A practical example or a more dramatic example, I would say, of that is we don't want to classify a business jet as an enemy jet just because of a small glitch in our sensor or a radar, for example. We want to be more patient with that because it can have disastrous consequences. Similarly, we've also talked about the concept of margin, the red line that we can get as a consequence of the perceptron as a very small margin for error. We typically want larger margins for error. And to do that, there can be interpreted in one of two ways. We want a classifier that classifies the two classes very well, but has a large distance from both classes. So that is what is the concept of margin. Another way of interpreting the same thing is in terms of the concept of regularization. And what that means that is that a small change in one of the features should produce a small change in the output. And that for a linear classifier means that the weights that we are using, the magnitude of those weights or the absolute value of those weights should be small. Because whenever one of those weights is either very large or very large positive number or very large negative number, then a small change in one of the features for a given example is going to produce a large change in the discriminant function score or f of x at the output. So we can say that structural risk minimization that minimizes these weights or equivalently performs regularization or maximizes the margin together with empirical risk minimization is going to do better than simple error minimization over the training data or empirical risk minimization only. So to emphasize that point, I'm just going to write that on this slide so you remember it better. So let's to rephrase, empirical error minimization is simply error minimization, error minimization over training data. Okay, so this is this thing. Okay, so empirical error minimization. We want to do more than that. And the more thing, the additional thing we want to do is that we want to maximize the margin of error, or we want to maximize the regularization, or we want to minimize the individual absolute weights of a linear discriminant to achieve this maximum margin, to achieve more robustness to noise. And this concept proposed by Vladimir Vapnik is called structural risk minimization. So you can think of structural risk minimization is equal to empirical risk minimization plus regularization. Okay, so theoretically speaking, empirical risk minimization plus regularization is called structural risk minimization, and this forms the basis of support vector machines. So if you think at a very high level, or if someone asks you, if you walk into an interview and someone asks you, what is a support vector machine? You can simply say that support vector machines are linear classifiers that produce the optimal separating boundary, or more precisely, they find such a weight and a bias that minimizes classification error over training data, empirical error minimization, just like perceptrons, but they also maximize the margin, or equivalently, they maximize the regularization, or equivalently, they minimize the individual absolute weights so that a small change or a small error in due to measurement, for example, will not have a large effect on the output of the system. Okay, so now we are going to use these concepts to build the mathematical representation of support vector machines. So in terms of representation, the, the representation of a support vector machine and a perceptron is exactly the same. We get a set of features which are denoted by x1 to xd. We have if we have d different features, and then the discriminant function is still linear, so it's still a dot product of w transpose x plus b. So that's good, nothing different there. What changes is the evaluation part. Remember, in a perceptron, the loss or the error over the training data set is calculated by the sum of these errors, the errors based on the Haynes loss function, for example, over individual examples. We've talked about that in pretty much in quite a lot of detail in the previous slides and in the previous lectures. Okay, so this is nothing new. This is the same thing as a perceptron would have. What's additional is this bit. So this is structural risk minimization. Remember, it has this empirical error minimization, but it has this something else as well. And that something else is essentially, this is the formula for that something else. It's called regularization, but what it is essentially is it's a sum of the weight values, or the square, more precisely, the sum of the square of weight values of the linear discriminant. The important thing to notice here is that this part on the right hand side, this error part, is based on the training data. It's based on X and it's based on Y, which is the input features and the labels. Whereas this regularization part is based only on the structure or the structural components of your classifier. In this case, it's based only on the weight parameters of your linear discriminant. It does not have any terms related to the data. So that is why this is called structural risk minimization, because it minimizes the empirical error as well as it minimizes some structural characteristics or introduces some desirable structural characteristics that we want to optimize over. Okay, so that's why it's called this structural risk minimization. And the reason it has this formula is very simple. Remember, we said that we want a classifier that does not produce a large change in its output whenever there is a small change in its input. And one way of doing that is to minimize the overall is to minimize the each of the weight values or the absolute weight values. Because if a weight value is small, then if even if the feature changes by a small amount, it's not going to produce a large change in the output. So we want small weights. And to do that, what we can do is we can minimize the square of the individual weights, because whenever the square of the individual weights is going to be small, it's going to the overall weight is going to be small, whether it is positive or negative. So that's why we have this as a regularization term. This 1 over 2 part over here, that's just going to come in handy when we are going to take derivatives, when we solve this optimization problem that's written in front of you using gradient descent. There's nothing more than that. You can probably just ignore that. Okay, so if you don't want to consider this 1 by 2, you are free to do that. If you pay a bit more attention, we can say that W1 square plus W2 square plus up to so on plus WD square, these D features, you can express that in a more compact manner by taking the dot product of W vector with itself. So the first term gets multiplied with the first term, so that gives us W1 square, and it's added to the product of the second term with itself, so W2 square and so on. So we can probably write it like this. Another even more compact representation is to write it in terms of the norm of W vector. Remember, the norm of a vector W, let's say, is nothing but W1 square plus W2 square, W2 square plus up to so on WD square under the root. Okay, so if you take the square of this, is essentially becomes this thing. So all these three things are equivalent. And now we also understand the reason why we have that. We want a classifier that minimizes a notion of error over the training data set. In this case, is defined using this hinge loss function. So this is the same thing that we talked about when we were talking about perceptrons. So this is hinge loss over individual examples. There are n examples in total. And what we are defining is that this loss function, this thing, this error that we are trying to minimize, is simply the average error across all of those training examples. It's nothing new, the same exact concept as a perceptron. Other bit that we introduce is this regularization bit. That is, we want to minimize the sum of the squares of the weights because we want small weights. Okay. However, these two criteria, we have now two criteria. One of them is this RFF, and one of these is LFL, and we understand both of them individually, right? And I hope you have a good idea of why we want to do both of these. Now, the next bit is, if you pay attention, there is a small thing hiding here, which is a parameter called C. Okay. Now, if this is a parameter that you would need to set. It's going to be a non-negative parameter. It's called weighting factor. Some people call it a hyperparameter. Remember, the parameter of a classifier are the weights and the biases that we have. And then this becomes a hyperparameter because this is something that is not optimized. It's something that you need to specify. Let's say if you specify this equal to 1, then this equation becomes 1 by 2 W transpose W plus the summation 1 over N, the summation of this loss function, which is max of 0, 1 minus yi into f of xi. Okay, so we can have this I is equal to 1 to n. So this is the average error using as measured using Lehigh loss. This is the regularization term. And we are equally weighing these two terms in the minimization equally. If I want to do more error minimization, if we want to turn the support vector machine into a perceptron, then I can set a very large value of C. So that is essentially going to get rid of this term. So, so think of it like this: if you have two different objectives, let's say you want to maximize your grades, but you also want to have more fun, and that becomes your overall objective function. Then the more weights you assign to one of them, and you optimize the more you optimize that particular component of your life in this case. And if you relate it to the same thing over here, this parameter C over here controls how much weighting do we want to give to the error minimization or loss minimization over the training data, that is the empirical risk minimization, and how much importance do we give to this regularization. If I don't want to give any importance to the regularization, I would set a very large value of C. If I want to give a very large, to a lot of emphasis on regularization, then I'm going to give a very small value of C. Okay, so those are the two. That is the effective role of this parameter C. So it controls the relative contribution of of this regularization term or this error term. So the mathematical representation or the optimization problem underlying a support vector machine is this thing. Remember, we started off with why we should be doing that. We should be doing this bit because we want to minimize error over the training data set because that allows us to learn from data. And then we want to do this because that allows us to give good noise tolerance or introduce regularization, or it also allows us to maximize margin. Now we can control the two parameters. It's a delicate balancing act by choosing an appropriate value of this parameter C. Don't confuse, get yourself too confused about the role of C at this time. We're going to understand that through examples as we go along. Understand it at a higher level. We want to minimize error, hence the minimization of this loss function on this side, on this right side, much like what we had in the perceptron. And the only additional bit we got is this 1 by 2 W transpose W. So if we compare and contrast, let me compare and contrast a support vector machine and a perceptron. So a perceptron just solves the following problem. It minimizes, or it finds such weights that minimize the hinge loss function for all of the training examples. Okay, so this is what empirical error minimization does, or what a perceptron does. It finds a line that gives the minimum error. It can be a line that does not have sufficient margin, and that's bad. Whereas a support vector machine does structural risk minimization, which is proposed by Vladimir Vapnik back in the 60s. And that does two things. First of all, it does the exact same thing as a perceptron, that is, it minimizes the loss over individual examples, individual training examples. So I'm just going to add 1 over n and I'm going to multiply c. So those are just scaling parameters. Don't worry too much about those. And then it also does this thing. And what that introduces is a structural component to this optimization problem. And that gives rise to maximum margin, as we're going to see. We're going to actually go ahead and prove that minimizing this bit with respect to the margin, with respect to W, is actually going to give you the best margin. And we have covered that intuitively because if you have a small value of weights, then the classifier is not probably going to change its output label whenever there is a small change in the input. So the only difference between a perceptron and a support vector machine is that a perceptron uses empirical risk minimization and SVM uses structural risk minimization. So perceptron goes to ERM and an SVM goes to SRM. And this is going to be more robust. It's going to give us better generalization. So I hope, without sounding more like a broken record now, I hope you have a good understanding of why we want to do this. Okay, because that's what we are going to do is we are going to solve this optimization problem. Okay, so remember, this is the optimization problem that we got as a consequence of SVM. And we are going to do a small trick, and that shouldn't confuse you too much. So instead of having a parameter C over here, alternatively, what we can have is we can associate a parameter over here that we can call lambda. So instead of it would have the same role, first of all, as this parameter C. If we choose a large, but it would have the exact opposite effect. So if we choose a small value of C, then what we are doing is only this uh, margin maximization or this regularization bit, this bit over here. Uh, and that is in contrast to this the role of this lambda. So when we have a large value of lambda, all we care for is going to be this regularization and not this error minimization. So these are going to have the exact opposite effects, but they are logically very closely related. So C is inversely proportional in its effect to lambda. So don't get yourself confused by this small change. We can either use, some books use the parameter C in the formulation of a support vector machine, and other books use a lambda with this W. So both of them are going to have a similar effect, but exactly opposite. I hope you understand that. Okay. So that means that we can express this optimization problem as this optimization problem over here. Okay, so no, the only change is instead of a C over here, we have introduced a lambda over here. Remember, both of them essentially control what is the role of each of these two terms. Okay, now we have got a clean mathematical representation of this thing, and we want to solve this optimization problem. And we have an algorithm, gradient descent, of course, that we can use. So that means that we want to calculate the gradient of this term, this objective function that I've denoted with P. We want to calculate the gradient of that, and then we want to take a step by an amount alpha in the direction opposite to the gradient. So this is the gradient descent algorithm. So we want to use this algorithm to solve this problem. Okay, and that's what we are going to do. If we take the derivative of P with respect to W, then because this is W transpose W, so you can think of it in terms of W square if W is a scalar. So what that would mean is if we take the derivative of W square, right? So this is lambda by 2 W square. So if you take the derivative of this thing, this lambda by 2 W square, it's going to come out to be uh, 2 times, so sorry, lambda by 2 multiplied by 2 times W. So this 2 goes with this 2, so you'll end up with lambda times W. And with some loose and hand waving mathematical abuse of notation, you can probably guess where we got this W. When we take the derivative of, or when we take the gradient of this P, which has lambda by 2 W transpose W, we end up with lambda W over here. And this bit over here, if we choose a single example rather than all of the examples, and we take the derivative of this thing with respect to P, or if we take the derivative, we've already done that as part of the perceptron learning algorithm, we essentially end up with this thing. Okay, so we get the gradient equal to 0 whenever there is what is called a margin, when there is no error or no misclassification, we get this thing. And if there is, so we get a corresponding error over here. Okay, so we know we already calculated this as part of our calculation of the perceptron. So this is nothing new, and we can combine these two and we can write it like this. Write it like this objective function. So this is going to be the gradient. So this is going to be lambda w, and then this is going to be the same thing as we got for the perceptron. Okay, and then that gives us this equation, and I welcome you to work this to solve this by hand. How do we take the gradient of this and how do we end up with this? Please, if you want to go ahead and pause the video at this time, I would welcome you to go and try to solve this by hand. It's not tricky. It's just going to be some very simple calculus. If you can take the derivative of the square function, you should be able to do that because we've already covered why the derivative of the hinge loss function is this much when we were covering the perceptron video. So this one over here indicates an indicator function that produces one whenever this condition is satisfied. So this is essentially a compact way of expressing this piecewise function like this. Okay. So what this allows us to do is then go ahead and write this algorithm as part of a course. So the only thing that we need to change in terms of converting us the perceptron code that we had written into the support vector machine code is to introduce this one line. That's it. Okay, and that line is coming because of the additional W transpose W arrangement that we added to the objective function, and that's pretty much it. So the only difference in terms of the code is the introduction of this line over here. And that line essentially reduces the value of the weights while it's training. Okay, so if you continue it for a number of epochs, it's going to perform what is called a regularization update. So the equation, the mathematical equation that we developed over here, it gets translated into a single line. So all that mathematics into a single line of code. Okay, so I hope you're able to understand that. If not, it's really easy. Break it down into simple steps. Think about how we move from empirical risk minimization onto structural risk minimization and what was our motivation to do that. And then the rest of it is simply formulating it as a problem, as a optimization problem, and then trying to solve it using gradient descent. So the only addition that we get is this line. And if we add this line to our code and we execute that, we can clearly see the difference that we see between perceptrons and between and the support vector machine. If we use these four data points, 1, 2, 3, 4, and we train the perceptron, we get a boundary like this blue line that you see. Okay, and I'll be providing the code, and you're welcome to execute it on your own. And as you can see, this does not have a lot of margin. However, on the other hand, if you use the same data and you add this one line of the code to the perceptron code, you end up with this beautiful line, which is at a maximum margin uh, from the two classes, or it has at least a better margin in comparison to the perceptron. So this is the conceptual difference between support vector machine and a perceptron in terms of the code itself. So this is a very good demonstration of what's going on. We'll be talking about what is the role of what is the cost of dimensionality in another lecture. But right now, what we have done so far is we wanted to have maximum margin, and we got it. We got it by trying to rewrite the optimization problem of a perceptron by introducing a very simple regularization term, and that is 1 over 2 W transpose W. Small weights would result in a small change whenever we have noise, whenever we have a perturbation in the input that leads to robustness and that can lead to better generalization. So this was the idea proposed by Vapnik when he proposed the support vector machines. Okay, so what we have covered so far, if you've not been able to follow the mathematics in too much detail, that's perfectly fine. What we've covered so far is we've covered support vector machines. Support vector machines in their basic form are linear classifiers that give maximum margin. So they are lines that are the maximum difference away they can be in between the two classes. And the principle of operation is based on what is called structural risk minimization. A lot of other modern machine learning methods are also based on structural risk minimization. That's why it's so important to understand support vector machines at a conceptual level before moving on to more complicated models like neural networks or deep learning neural network, deep learning and all that kind of stuff. It's really important to spend some time on this to develop your conceptual foundations. Why it's important to go from empirical risk minimization to structural risk minimization, like the support vector machine does. So it does this minimize the number of training errors, and it achieves that by minimizing the hinge loss function. It also maximizes the margin by introducing this term in its optimization problem and then minimizing it. So it has two parts. One of them is the minimization of the loss over individual examples, and I'm going to just call it yi f of xi, okay? And then it has a regularization component as well. So once we have these two, we get a support vector machine. But there is a limitation, and if you want to pause the video at this point and think what that limitation is for support vector machines, please do that. And I hope you have come to the conclusion that just like perceptrons, support vector machines are also linear classifiers. They're not able to generate nonlinear boundaries. Okay? And that is a major limitation because not everything is going to be beautifully linearly separated. We've already seen a few examples, such as the exclusive OR example, which is not linearly separable. So what we want to do is do nonlinear classification. And then there is a trick that allows us to transform any nonlinear any problem that is not linearly separable into a linearly separable problem using something called the kernel trick, and then we are able to solve any problem that may not be linearly separable using support vector machines. So, so support vector machines are can be linear classifiers if you're using a linear discriminant, and they can also be nonlinear classifiers through what is called the kernel trick. We haven't covered that, and then we can essentially solve any machine learning problem, any classification problem that is given to us, and we it's theoretically guaranteed. We haven't gone through the math of that. That shows that support vector machines are actually better classifiers in comparison to perceptrons. Okay, so we're going to stop here, and I welcome you to play with support vector machines. This is a very good tool, uh, and if you click on this link, then it allows you to use support vector machines in the form of an applet. Okay, this is a very simple tool to understand support vector machines. What it allows us to do is is to use it to make some data points like this one, and then you can specify another class, and then if you run the support vector machine, it simply generates the boundary or the classification boundary that would be generated by the support vector machine uh, after optimization. So you can either execute the code that I've provided you as part of this module, or you can also get a better understanding of this using this particular tool. Okay. So next time, what we are going to do is we are going to try to understand support vector machines The hyperparameter C that you had there, or the lambda that we replaced it with, we are going to understand the role of that in a bit more detail in the coming lectures. Okay, thank you.